So, thank you for inviting me to have this talk. I just have some cheat notes here because I couldn't remember the whole speech. But yeah, my name is Racin Nygaard, and I'm a first-year PhD student at the University of Stavanger in Norway. And I have a master's degree in computer science, and in my thesis I studied blockchain storage systems. And currently I'm researching the applications of blockchains and with a focus on storage systems. So I'm here today because I believe that we are researching many of the same things, and I hope that it's possible to collaborate on to overcome some of these challenges. So my talk will be first to talk a little bit about the project which I'm associated with in the university, and then I'll go sort of over informal introduction to proof of storage, and then try to develop this idea from proof of storage into how it can be used in with the blockchain to form a reputation system, and then I'll try to even further develop this and how it can be used in an incentive scheme to increase node participation. So BBChain, it's the project, research project, which is a joint effort with the University of Stavanger and the University of Tromsø, and it's funded by the Research Council in Norway. So part of the BBChain project is to design a global academic database of student degree records. And there's two main tasks in this project, and the first one is to verify document authenticity using biometric signatures, and the second one is to ensure the permanent and verifiable storage of the degree certificates. So my job in this project is to focus on the challenge of ensuring that these degree certificates it's permanently available, and one of the challenges which we have is that these degrees might not be accessed for several years, and in our design we have sort of separated the storage layer from the agreement protocol or the consensus, and additionally we designed the system without making any trust assumptions on the storage nodes, and therefore we believe that the only way to sort of ensure that the data is still there is to use the proof of storage algorithms. So in the simplest form, the proof of storage algorithm is a protocol between an owner and a storage node, where a data owner is asking the storage node if it's holding its data or not. So the storage node could either reply yes or no to this answer, but the problem here is that we do not have any trust to the storage node, so this answer doesn't tell us anything. And another solution would just be to send back the entire file to the owner and have him run the integrity check on his own, but this has a significant bandwidth cost. So instead we design an algorithm based on probabilistic proof, where we only ask the storage node to tell us parts of the file, and if the storage node is able to answer the probabilistic challenge correctly, we can infer that he has the whole file. So the storage node can either answer the probabilistic challenge correctly or incorrectly, but if the storage node knows for sure that he doesn't have the data, he will most likely just stay silent and don't answer anything. So the informal definition which we use for proof of storage is just to check if the storage node has the data, and there are many properties which we want in this scheme, but the most important one is that it should be impossible for anyone to construct a valid proof without being in possession of the data. And the second property which we have listed here is that it should be able for other ones than the data owner to issue these challenges. And the reason which we want this property is so that the owner can sort of delegate this task to other nodes, and then he can sort of upload this data and forget all about it. And in Swarm, this algorithm is, you call it proof of custody. It's basically the same thing. And yeah, you can read more in the Smash Proof paper for the details there. But now I'll just go through like a simple protocol, which is not really practical, but just to highlight some of the properties which we need to sort of develop this into an incentive scheme. So first off, we need to handle these incorrect responses. So when the owner issues a probabilistic challenge and the storage node answers incorrectly, what can the owner do? Obviously, it's a big problem for him because now his data is lost, but in a system, he can also maybe broadcast this message to the other nodes so that at least no one else stores the data with them. But what happens when the storage node has the data, but the owner still claims that he doesn't? So the storage node in this case can also claim that the owner is lying, but for a third party listening in, it doesn't give any value because he has no idea who he should believe. So therefore, we need this property called public verifiability. And the idea behind this is that you can verify both the messages given by the owner and the storage node. So it's possible to verify both the proof and the challenge, but here I'll just show you an example how you can build a public verifiability for the proof using the blockchain. So we have the same protocol, but now instead, initially the owner writes the expected proof he wants onto the blockchain, and then he queries the same probabilistic challenge, and now the storage node also writes the proof to the blockchain. And then this third party can just check the blockchain, and he will immediately know what was the challenge, what was the correct proof, and from there decide who is correct. But obviously this is not the most practical solution because writing to the blockchain is expensive, both in terms of the computation that you need and also there might be some transactions cost. So to overcome this, we want to minimize the amount of data we need to write, and to do this we can sort of infer the correct responses, and again we can start off by the owner writing the expected proof, issuing the probabilistic challenge, but now the storage node can just put his answer into a digital signature or use the digital signature to sign the answer, send it to the owner, and then the third party can listen in and see that there's no complaints there's not been any complaints given about the storage node, and then he can just assume that he's behaving correctly. But if the owner finds out that actually he's not behaving correctly, he can put this signed answer onto the blockchain, and the third party can then listen in. So when you're inferring this, you are making the assumption that there will be much fewer incorrect answers than the correct answers. And this assumption here is, of course, that if he's only giving incorrect answers, he's not having a lot of revenue anyway. So to build the reputation from the proof of storage, we sort of realized that the proof of storage gives us both a measure of integrity and availability. Integrity, because that's essentially what you're checking with proof of storage, and availability, because only those nodes who are online is able to respond in a timely fashion. And with this public verifiability property, only those nodes, everyone in the system is able to check the challenges and the proofs given, and from there they can infer the behavior of the storage nodes. And if anyone read the Kademlia paper, here they claim that a node which has been online, or the longer a node has been up, the more likely it is to be online for another hour, and we sort of make the same assumption for reputation. So to illustrate how this reputation scheme could work is that we have 3 possible events: a correct response, a no response, or an incorrect response. And each of these affect the reputation of the nodes. Here I just assume that they are linear, but there should be some more complex function, because the consecutive events matter here. So anyway, the nodes start off initially, and from each block, which is the answers are inferred for each block, then the reputation of each node changes. But just to clarify, it's not the actual data written to the block, it's just what is inferred by the third parties listening in. And also here I've written that there's sort of one every day, but this is not necessary either. It's just to sort of clarify that there should be some causality between these events. So we believe we can use this to sort of build the incentive scheme, and our goal for the incentive scheme is that we want to have an interactive system which motivates correct behavior. And also we believe that to increase the participation, we must open the system to the diverse participants, so that not only those with very high bandwidth or very high capacity can join, but the threshold for joining should be much lower. And we're also looking at a scheme which do not require you to have such a large deposit, because we think that if you require a very large deposit, then you might exclude some participants, because they might not be willing to put up so much money, because they could just go and invest it elsewhere. So we realized that, of course, it's a decentralized system. We cannot use simple fault-tolerant models. We need to use a Byzantine fault-tolerant model, and we also have the constraint in our internet system that any node can join and leave at any time, and they can just create a new identity. And then there's not any, you cannot put a claim to a node, because you can just recreate this identity at any point. So in our vision, we need to use the bar model, and here we have 3 actors. The Byzantine nodes, which are sort of can arbitrarily fail at any point. The altruistic nodes, which always follow the protocol and behave correctly. And the majority is rational nodes, which only does what benefits them. So to get the rational nodes to follow the protocol, we need to have an incentive scheme which benefits them. So the incentives in the fundamentals is that it's a way to either encourage a correct behavior in the nodes, or to penalize behavior we do not want. It's cutting out. Or a combination between them. So we also realized that there's an inherent cost from nodes to participate in the system, so the rewards must be at the minimum greater than the cost for participation. So traditionally in blockchain systems, the most common way is to reward out money. For example, in mining in Bitcoin, the more you mine, the more money you earn. But we sort of look at this reputation, and we see that this is sort of a way to sort of increase business opportunity, because in the real life, if you have a good reputation amongst your peers, then they are more likely to trust you or collaborate with you. And also we think that having a reputation gives you some kind of stake in the system if you are able to increase your revenue by having this reputation. And therefore we think that having a loss of reputation is sort of can be comparable to having the loss of a large deposit, as long as the reputation actually can generate some revenue for you. Yeah, so then I'll just want to give an real example of an incentive scheme in the storage market. So this is the real price examples taken from Store.j and Dropbox. And there's some misalignment of the terms here, but just to clarify that for Store.j, the amount given at the bottom is how much the storage node can earn. But for Dropbox, it's how much the client has to pay. So in all these examples, there's 1 terabyte of data stored. So in Store.j, they have this fixed pricing thing, where they have defined already how much you earn for storing per terabyte of data, and also how much you earn for serving any data. So the example to the left, we have an archival node, which is just storing 1 terabyte of data, and there's no upload or download, just the necessary proof of storage challenges. And in the streaming example in the middle, there's 6 terabyte of monthly access, and this means that you're able to download your full 1 terabyte of data 6 times. And here the node is actually earning $128. And the reason we chose exactly 6 terabyte is that on the Dropbox example, you are allowed to have 200 gigabyte downloaded every day. And if we multiply this by 30, you end up at sort of 6 terabyte. So here you're paying only $9.99 for a similar kind of service. So the idea behind this is just to show you that if you have a fixed pricing scheme, it's very difficult to set the correct price, and you might end up being running yourself out of business because you're not very flexible, and you might also cater to a specific type of storage type. So in this example, it's much more beneficial to be a streaming type node than archival type node. And the other challenge here is that who is actually responsible for setting the price? And at least to me, it seems like there should be like some central authority which sets this price, and this is not exactly what you want in a decentralized model. So instead, we are looking into having a decentralized marketplace where the sort of both the owners and the storage node can compete for the price, and have the typical supply and demand model where the storage node publish the price for the service, and then the data owners and the storage node can sort of negotiate and come to agreement on the terms via a smart contract. And this terms is a very flexible notion, but in our example with the degree certificates, we want these terms to include some promises which encourages archival storage. So we have just made some model here with the potential earnings of the storage nodes, and the key idea here is that a node with higher reputation is rewarded more for serving the same amount of chunks. And as you can see on the very left there, the nodes have a very high potential earning, even though they are not serving any chunks. And similarly, nodes to the very far right can earn a large revenue, even though they not have a high reputation, meaning that they are not online all the time. So we believe that we need sort of some kinds of scheme like this to reward the nodes in our case, because our data will very rarely be accessed, and we don't want this kind of thing where nodes are able to delete the content which is not accessed very often, and then they can just get the content which is more frequently downloaded, and then we have a lot of things with how to have this litigation process and everything. But instead we want to sort of make the node unwilling to delete any data because he's rewarded more by just storing the data, which is not very often accessed. And then the problem here is, which you see at the bottom, the pink area, that this means that the node has too low reputation to be able to earn anything. And the question is, of course, how can a new node get into the scheme here? So we are looking at having some kind of proof when a new node joins the system that he has to sort of publish his computational power, his upload downward bandwidth, just to say that he is a strong node or a not so strong node. And the idea here is that the stronger node you are, the more or the less likely you are to just join the system and leave again for no reason. And also you sort of limit this possibility of a Sybil attack, where node can just create new identities to try to disrupt the system. So lastly, I just want to mention some of the research which I plan to do going forward. The first thing is to look at some ways where we can sort of move the task of challenging the storage nodes onto the storage nodes themselves, so that they are sort of responsible for proving to others that they are storing the data. Another is regarding with this reputation system I mentioned, where we think that there needs to be some kind of minimum frequency of the challenges which you issue so that you can maintain this reputation. And the study here is, of course, to find if there is a limit, and in case, what is the minimum frequency. And lastly, this privacy-preserving bullet point, it's not concerning the privacy on the blockchain or on the storage node, but rather what happens to the degree certificate after it's downloaded and shown to someone. How can you sort of limit the exposure of the degree certificate off-chain? So that's what I had for me. Thanks for your attention. If you have any questions, feedback, yeah. I'll also be at the hackathon.
Yeah, thank you for the presentation. In the beginning of the presentation, you have mentioned about the proof of custody. Could you explain it?
Yeah, you mean the proof of custody protocol?
Yeah.
Well, it's kind of integrate the whole protocol, but it's based on these Merkle proofs, and cannot not give you the exact protocol right here, but it's in the paper. And
so maybe any one link will be enough.
A link? Yeah, I can send you the link. It's
okay
on the Ethereum documentation.
Okay, thank you.
It's called the Smash Proof, the paper.
These also two questions related kind of to this. On which primitives are the proofs constructed? Is it per chunk, or are the chunks aggregated somehow? And second of all, is the system designed to be compatible with the Swarm building blocks? Or is it a standalone solution that you're presenting?
So here I'm just talking about sort of the general idea for our system that, well, to go back to your first, if it's per chunk or per file or aggregated, it sort of depends on what is the storage model, if it's only storing a chunk or if it's storing the entire file. And that's how you can build this proof. But I had some more slides, but I didn't have enough time. But the point is that you want to have as few of these storage challenges as possible, because they consume a lot of bandwidth and computation, so you want to aggregate as much as possible. So one idea we have is that even though a node is maybe storing a chunk from many different files, you can aggregate the whole challenge and just challenge the whole data set that the storage node is holding. Yeah.
Hello. This is just to complete the answer from Racin. Like, we came here, so we work together, and we are trying to build a collaboration with Swan. We don't know at this stage if we will have a separate system or we will build with Swan, but yeah, that's the idea of coming here, presenting our problematic, and see how can we collaborate together.
Any more questions?
So as I understood, it's about certificates. Do you prove who is the issuer of the certificate, and how do you do that?
That's actually the project of another PhD student who is not here. So the BBChain project actually includes like 3 sub-projects. There is a PhD student working on distributed systems and making a framework to facilitate the distributed systems to be developed in an easier way, because nowadays it's complicated. The second student is working on the verification, and he's now working on a smart contract. He was also studying the sovereign network, but currently is much more on the idea of smart contracts, but yeah, it's recently started. So, and Racin, who is working on the part of incentives and proof of storage. Yeah, I'm a postdoc there, and yeah.
Any further questions? Okay. Well, thank you very much, Racin.